Welcome back to the Deep Dive. Today, we are trying to settle a huge one, a real debate in industrial history.
Right.
What is the single biggest train ever assembled?
Right.
And we're not talking about your daily commuter train here.
Right.
We're talking about uh, the true leviathans of the rails.
The absolute giants. And it's a tricky question, because biggest can mean a few different things.
Exactly.
Are we talking longest, heaviest, or are we talking about the most powerful locomotive itself? Our mission today is to dig into all of that, to look at the machines that represent the absolute peak of industrial engineering.
Yeah, these are machines that look less like transportation and more like a moving city built to haul a mountain. We're going to look at the one-off tests, the big flexes, but also the daily workhorses that are, arguably even more hardcore.
They really are. And ultimately, this whole story is about pushing the absolute limits of physics. Just seeing how much stress a piece of steel can take before it just gives up.
Okay, so let's start with the undisputed champion, the trivia night winner.
Mm.
If you ever get asked, the answer is a massive engineering test from 2001 down in Australia. The BHP iron ore train.
That's the one. And it's important to frame it correctly. This wasn't a normal run. It was a one-time journey specifically designed to see what was physically possible.
And the numbers are, they're just staggering. It's hard to even picture it.
It really is.
We are talking about a train that was roughly 7.3 kilometers long.
Let that sink in.
That is 4.6 miles of continuous metal. For perspective, that's almost the entire length of Manhattan Island. A single train.
And the weight, of course, matched the length. Fully loaded, it clocked in just shy of 100,000 metric tons.
99,700 to be exact.
Right, spread across 682 iron ore cars.
So to move that 4.6 miles of mass, they needed 99 diesel-electric locomotives. But this is where it gets really interesting, right? The problem wasn't just raw power.
Oh, not at all. The real challenge, the core physics problem, was making sure the train didn't literally destroy itself the second it started moving or braking.
You're talking about slack action.
Precisely.
Yeah.
On a train that long, the time delay is, it's catastrophic. The brakes are pneumatic, right?
Yeah.
Air pressure. So the signal has to travel down the line.
And on a 4.6-mile train, that's not instant.
Not even close. It could take minutes for the signal from the front to reach the very last car.
So the front cars start slowing down way before the back cars even get the message.
Exactly. And that creates this immense compression wave. The cars slam into each other and then they rebound violently.
That's the slack action.
That's the slack action. And those forces, tensile and compressive, are so monumental they exceed the strength of the steel couplers. The train just rips itself in half.
So how did they do it? How did they make the BHP train work without it just snapping apart?
The key was a technology called distributed power control, DPC. So instead of putting all 99 locomotives at the front, which would be impossible, they've scattered them. They placed them at strategic points all the way down the 7.3-kilometer line.
So you have power units in the middle, near the back, all over. But how do you sync them all up? That sounds like a nightmare to coordinate.
That's the genius of it. One single engineer in the lead locomotive controls all 99 units remotely.
By radio.
By radio, yeah. The system constantly calculates the stress forces along the train and tells each remote locomotive exactly how much throttle or brake to apply almost instantly.
So when the engineer hits the brakes, the units at the back start braking at the same time as the units at the front.
Mm-hmm. It keeps the whole train under a constant manageable tension. It essentially makes it behave like one single cohesive unit instead of 682 separate metal boxes being dragged along. Without DPC, a train of that scale is just flat out impossible.
Which solidifies the BHP run as the record holder.
Great.
But like we said, that was a one-off, a test. What about the trains you might actually see running every single day? The real workhorses.
For that, we actually stay in Australia. The modern iron ore trains run by companies like Rio Tinto and BHP, they aren't 7.3 kilometers long, but they are still, they're jaw-droppingly huge.
We're talking 2 to 3 kilometers long on a daily basis. That's, 1.2 to almost 2 miles?
And weighing 30,000 to 40,000 tons, pulling maybe 250 or 260 cars. They've perfected that scale for continuous operation.
And it only works because of where they are.
Exactly. These are private, dedicated rail lines, super straight, minimal hills, running from the mines straight to the ports. It's basically a steel pipeline. No public crossings, no complex switching.
And they absolutely use that same distributed power control.
Oh, they have to. Even at 2 kilometers, the flak action forces would be more than enough to tear them apart without it.
But there's another one, a truly legendary workhorse that operates in maybe the most brutal environment imaginable.
Yes, for that, we have to go to West Africa, to the Mauritania iron ore train.
This thing is famous. It runs right through the Sahara Desert.
It is an absolute marvel of endurance. It's routinely around 2.5 kilometers long, about 1.6 miles, with 200 or so cars. But the environment is what makes it so hardcore. It's just sand and heat for hundreds of kilometers.
And I read something unbelievable about this train. The passengers.
Yeah, that's what makes it legendary. There's basically no other way to cross that part of the desert, so people will literally climb on top of the open-top ore cars and ride for the entire journey.
Just on top of the iron ore.
Right on top. Or wedged in between the loads. No shade, no shelter, just blistering heat, freezing nights, and relentless sand. It just shows you how vital that train is. It's pure, raw, operational muscle.
That's incredible. And it's a perfect shift for us because whether it's the BHP record or the Sahara Behemoth, the whole system depends on the power driving it. Let's talk about the locomotives, the actual engine.
And to do that, you have to start at the absolute peak of the steam era with a machine that is just iconic, the Union Pacific Big Boy.
The goat of steam, really, built between 1941 and 1944. This was it. This was the absolute endgame for steam technology just before diesel really took over.
It was built for one reason, and one reason only: to haul massive freight trains over the Rocky Mountains without needing a second helper engine.
And the stats are they're still unbelievable. It weighed about 1.2 million pounds.
600 tons with its tendon.
It was 132 feet long, making about 6,300 horsepower.
And the key to its design, the thing that made it work, was articulation. It had a 4-8-8-4 wheel arrangement.
Which means?
What, exactly?
It means the driving wheels were split into two separate powered engines under one giant boiler, and they were hinged in the middle.
Ah. So that huge, long, rigid machine could actually bend?
Exactly. It could navigate the curves of mountain passes that a single rigid frame that long never could. It was a masterpiece of engineering, the absolute zenith of steam.
And one of them, number 40014, is still running today. You can go see it. It's one of the largest moving historical artifacts on the planet. A direct link to that era. But once steam hit that peak, the power race immediately shifted to diesel.
Right. So now manufacturers are trying to create a single diesel unit that can outperform the big boy.
And that leads us to the first big contender, the EMD DDA-40X. Most people call it the Centennial.
Built for Union Pacific's 100th anniversary in the late 60s. And this thing was physically the biggest diesel locomotive ever built for regular service.
It was basically two powerful diesel engines bolted onto a single frame, almost 100 feet long, and it produced a staggering 6,600 horsepower. For decades, it was the most powerful single diesel unit in the world.
But the horsepower race didn't end there, did it? It peaked again in the late 1990s.
It did, with the GE AC6000CW. This was GE's attempt to make a reliable 6,000 horsepower unit. And the key here is the AC part. It used AC traction motors,
which gave it better grip on the rails, right? Better adhesion.
Far superior adhesion, especially when starting a heavy train from a dead stop. So technically, it was a huge leap forward. But the AC6000CW also kind of proved why the whole stupid big single engine idea was flawed.
How so? I mean, 6,000 horsepower in one package sounds efficient.
It sounds efficient, but in practice, it became known as a maintenance nightmare.
Huh?
The engine was so complex, so highly tuned, that it was difficult to work on and required very specialized parts. So if that one massive, complex unit went down, you lost your entire 6,000 horsepower in one go.
And you've got a very expensive, very heavy paperweight sitting on the tracks.
Exactly. And that brings us right back around to why distributed power is king today. The railroads learned a huge lesson.
It's better to have multiple smaller units than one giant one.
Far better. It is much more reliable and cost-effective to run 3 standard 4,400 horsepower locomotives spread out along the train. If one of them fails, the other 2 can probably still get the train where it needs to go, and that failed unit is way easier and cheaper to fix.
So the idea of distributed power didn't just solve the physics problem of slack action, it also solved the economic problem of maintenance.
Absolutely. The modern megatrain is a combination of everything we've talked about. The brute force of the big boy era, the high horsepower from the diesel race, and the smart, reliable control systems perfected in the 2000s.
Okay, so let's do a quick power ranking for everyone just to make it crystal clear.
Let's do it.
Biggest train ever, by length and weight, no question.
Fair.
The 2001 BHP iron ore train in Australia. 7.3 kilometers.
The biggest locomotive ever built, the King of Steam, the Union Pacific Big Boy from the 1940s.
And the most powerful single diesel units, like the Centennial and the AC6000 CW, they were amazing, but they ultimately taught us that a fleet of smaller, smarter units is better than one big giant.
It's a really compressed timeline when you think about it. Peak steam in 1941 with the Big Boy, the massive diesel push in the late 60s, and then the all-time length record in 2001. A huge amount of innovation in a pretty short time.
An incredible story of just relentless mechanical progress.
It is. And here's a final thought for you to chew on. Think about the human element in all of this. Imagine being that one single engineer in the cab of the BHP train, remotely controlling 99 different locomotives spread out over 4.6 miles. What does that say about the sheer logistical trust involved, knowing that you, and you alone, are responsible for managing the physics of a 7-kilometer long line of steel with nothing but a radio signal?